Today, I'm very happy to speak the high performance of our photothermal AFM-IR technique and its capabilities in doing nanoscale chemical analysis. So yeah, beside myself and Jinky, I want to mention a few other people in the nanoIR team at Bruker. Martin Wagner and Chunzhen Li, they are two development scientists in the team. Cassandra Phillips is the nanoIR product manager. Peter DeWolf is the director of technology in charge of research and development. I also want to take this opportunity to thank every other nanoIR team member at Bruker, my former colleagues at Analysis, and also the nanoIR collaborators, advisors, and customers for their contribution to this fast-growing field. Thank you. So in this presentation, I will first introduce Bruker's photothermal AFM-IR, briefly talking about the technology, different AFM-IR modes, and also the current products. Then I will move on to the high performance AFM-IR. This includes the high sensitivity that we can achieve good signal to noise for sample less than 1 nanometer thick on non-metal substrate. And for high spatial resolution, we got some recent results that can demonstrate better than 2 nanometer spatial resolution, and we want to share these exciting results with the AFM-IR community. The AFM-IR technique can achieve controlled probing depths and also high surface sensitivity in some mode. And it can also achieve high speed for the measurement. This applies to both IR imaging and also fast spectroscopy. With the AFM-IR technique, we can get artifact-free measurement by using the phase-locked loop to compensate the mechanical artifact. And for correlative study, we can do mechanical, thermal, electrical, magnetic measurements for the same sample. And this has been the topic of a previous webinar. And Bruker's AFM-IR excels in every aspect of this list. And I hope by the end of this webinar, I can convince you that Bruker's photothermal has the highest performance in the world. Bruker has a long history developing the AFM-IR modes, and the first AFM-IR paper demonstrating nanoscale resolution was published by Professor Alex Dazi and his colleagues in 2005. Alex has been a very close collaborator with us from that time. And the first generation nanoIR was commercialized by Analysis in 2010. And in 2013, the second generation nanoIR 2 was developed. And soon after, the resonance enhanced mode became available that can achieve the monolayer detection. And in 2016, we developed the liquid mode AFM-IR and also the tapping AFM-IR. With this new mode, tapping AFM-IR mode, it can achieve better than 10 nanometer lateral resolution. In 2017, the hyperspectral mode is released. And in 2018, Analysis joined Bruker, and in the same year, the third generation nanoIR 3 was released. In 2019, we developed the broadband nanoIR 3S mode, and with that, it enables both scattering SNOM and AFM-IR at the same time. And in 2021, we had the new product, IconIR. It is based on the Bruker's Icon platform and has the highest performance for AFM-IR measurement. And also, we released the surface sensitive mode that can achieve higher surface sensitivity than any other AFM-IR mode. So Bruker has patented all the major AFM-IR modes. Resonance enhanced, tapping mode, and surface sensitive mode. And we continue to develop new AFM-IR modes and new capabilities. So ever since the release of the first generation, we have seen a rapid growth of the AFM-IR technology. And this shows the number of publications turned out by Google scholars. And you can see by the 2023, last year, there is almost like it is approaching like 2 publications per day, and that is like 700 publications for the year. And that is a very fast growth for this exciting field. And in terms of applications, the AFM-IR technique has a wide range, and that includes the polymer and to the life science, and also from like a semiconductor to 2D material, and also many other fields. And pretty much any field that can benefit nanoscale chemical analysis, we would like to use this technique. And the nanoIR customer, like they are very successful and doing very leading research in their fields. So how does the AFM-IR work? So it is very easy at step 1, 2, 3. So in this one, this is the FM probe, and this is substrate and the sample, and the IR laser pulse IR beam come to the sample under the tip. Okay, and if the sample has absorption at that wavelength, is going to do heat up and expand. Okay, so this shows the expansion of the sample. That's what we called like a photothermal expansion. Okay, for the technique. And this expansion will apply a mechanical force on the tip and cause the FM cantilever to oscillate. And we record the oscillation of cantilever as the AFM-IR signal. So because we detect the signal and it is proportional to the absorption coefficient. So in this way, we can get, when we plot the AFM-IR signal as a function of the wavelengths, we can get a spectrum that will correlate very well with the traditional FTIR spectrum in transmission mode. So AFM-IR detects photothermal expansion, and the spectrum correlates directly to the FTIR spectroscopy. Okay, and the physics is very well understood and documented by hundreds of publications. Now I probably can say by thousands of publications. And the FTIR library, such as the wireless know-it-all, can be directly searched to find good results. So here I show like the comparison of AFM-IR spectrum and FTIR spectrum for the sample Nano 6. And it is for the data, AFM-IR data was collected from the Nano 6 film, and it covers a range like from 800 to 3600. So pretty much like a big chunk of the mid-IR region. And in that way, it covers the fingerprint range and also the high wave number range. So you can see that in this whole wide range, the correlation between the AFM-IR spectrum and FTIR is very impressive. So we mentioned that Bruker has patented a few AFM-IR modes. So what are the modes? Okay, the first one is the resonance enhanced AFM-IR mode. In this case, that the cantilever is in contact with the sample, and the laser pulse rate is tuned to match one contact resonance of the cantilever. And for this mode, we can achieve like as good as 20 nanometer lateral resolution. And we have also like have reports that our users report like better than this number. But for most sample, this is like typical, tens of nanometer lateral resolution. And for this mode, it's very easy to use. And because it's direct sense the photothermal expansion by the cantilever and giving the resonance enhancement. And the next one is the tapping AFM-IR. In this case, the probe is working in tapping mode, and it is driven at a higher resonance, let's say, or lower resonance, F2, and the signal is detected at a different resonance, F1, and the laser pulse rate is tuned to match like a sum or difference of the two tapping resonances. For this mode, you can achieve like a better than 10 nanometer resolution. And also because it's working in tapping mode, it's great for soft sample that you don't want a lot of like force applied to the sample. And the third one is the surface sensitivity AFM-IR mode. So this one also uses a non-linear excitation mode, similar to the tapping AFM-IR. But here the probe is in contact with the sample, and also the laser pulse rate is tuned to match like sum or difference of like two contact resonances. And we can also achieve like a better than 10 nanometer lateral resolution. And for this mode, it has the highest surface sensitivity. So it's the best for the top layer analysis. And the last one